My name is Andreas Malmendier, and I'm an associate professor in the core math group at Utah State University. My research focuses on Calabi-Yau manifolds and the role they play in string theory. Recall that string theory is one of the most promising candidates to unify general theory of relativity and quantum mechanics. At the end of the 20th century, scientists discovered that there's not just one superstring theory, but several. They can be considered the limits of one big theory known as M theory. Interestingly, they are expected to be related by what we call string dualities. And one of the major themes in my research is to exploit the physical prediction of the existence of these string dualities to come up with some exciting new mathematical construction. The other important notion you need to know is the notion of extra dimensions. When Einstein designed his original general theory of relativity, it was meant for a four-dimensional spacetime. However, already shortly after, physicists and mathematicians started to design theories with more space-time dimension. For example, Kaluza and Klein came up with a five-dimensional space theory where the extra dimension was meant to geometrically encapsulate the existence of electromagnetism. However, to actually shield this extra dimension from being visible in our real world, they wrapped it on a compact circle and made that circle really small. Now, we use the same notion of extra dimension and compactification in string theory. Most superstring theories are meant to live in a 10-dimensional spacetime. And to actually obtain a realistic four-dimensional physical theory in the end, we need to wrap 6 of those extra dimensions on special shapes known as Calabi-Yau manifolds. Now, the name Calabi-Yau manifolds is based on the amazing work of Calabi and Yau. And actually, Calabi-Yau manifolds don't just live in 6 dimensions. They can be obtained in every even dimension. But the idea is, if you wrap those extra dimensions in a superstring theory on maybe a family of Calabi-Yau manifolds, you can obtain a realistic four-dimensional physical theory. Now, those shapes, these Calabi-Yau manifolds, not necessarily just in 6 dimensions, are a central focus of my research. In 2 dimensions, the topological shape of a Calabi-Yau manifold would be just that one of the surface of a bagel, which we call a torus. Now, already if you go to 4 dimensions, the simply connected Calabi-Yau manifolds are known as K3 surfaces, and they have a lot of interesting properties regarding their symmetries, regarding the families they appear in. And if you go into higher dimensions, 6, 8 dimensions, we know many interesting examples of Calabi-Yau manifolds, but there are a lot of interesting open mathematical questions. Even more interesting, the notion of those string dualities I mentioned earlier on give us a lot of interesting mathematical conjecture about how those mathematical objects should be related. And some of those most interesting conjectures are still open. Now, my research is exactly situated at the intersection of mathematical physics and algebraic geometry. For example, in recent years, I've constructed new families of K3 surfaces and also Calabi-Yau threefolds, and explained the relation and their construction in terms of families of algebraic curves. I've also described these families of Calabi-Yau manifolds in terms of what are known as modular forms and differential equations that govern the so-called period integrals. I've also used the expected existence of physical string dualities to obtain some interesting new relations between those mathematical objects. If you have any more questions about my research, if you are interested in it, please don't hesitate to write me an email.